Okay, so this video is the second part of chapter 8. We're going to talk about interaction between independent variables. So thinking about the slope, we probably can think about there are ways to make it nonlinear. So before this part, we talked about that the slope can change across different values of x. Now, interactions, we want the slope to change across different values of other variables. Okay, so how do we actually model it? We believe that perhaps a class size reduction is more effective in some circumstances than the others. And perhaps a smaller class help more if there are many English learners who needs individual attentions. Okay, so the argument here is that the slope for STR is higher in higher English learner school districts, but becomes smaller in lower English learner school districts. Okay, so if you want to write it in mathematical terms, it is delta TestScore divided by delta STR. So we think of this as the slope. Okay, what is slope? That is the effect of STR on TestScore. It's gonna depend on another x variable. We call it percentage of English learner. And so more generally, it is delta y divided by delta x1 might depend on the value of x2. Or we think of the beta 1 might change in different values of x2. So how do we model such interaction between x1 and x2? Again, we have three different circumstances. We first consider the x variable to be binary. Okay, so that is the first example, interactions between two binary variables. We have D1 and D2. Originally, they should be X1 and X2, but in this case, we use D to define it because we want you to have a clear idea that these two X variables are binary. Okay, you can write it as X1, X2, that's fine. But in this case, we use D1 and D2 to indicate that these two are binary variables. Okay, so D1 can be 0 and 1, D2 can be 0 and 1. And how about Y? Y can be anything. Y can be binary, Y can be continuous. It doesn't matter. So here we want beta 1 to depend on D2. Okay. Or we want the effect of D1 on Y to depend on the value of D2. And to allow the effect of changing D1 to depend on D2, we include an interaction term called D1 times D2 as a regressor. Okay, so now we have a new multiple regression that has three variables. Okay, the first variable is D1, the second variable is D2. The third one, you can think of it as S3. S3 equals to D1 times D2. So how do we interpret it? There is a general rule again. If you, let's say now you want to have a before and after. In the before, D1 equals to 0. D2 equals to lowercase d2. So uppercase D1 and uppercase D2 are the variable names, while lowercase d2 is a value that you don't know. Okay, it can be 1, it can be 0. We don't know, but we just use a lowercase d2 to represent it. So in the case when D1 is 0, expectation of Y equals to beta 0 plus beta 2 times lowercase d2. The reason why we only have two terms is because D1 equals to 0. So the second term and the third term disappeared, okay? And because we are taking expectation, so expectation of U also equals to 0. All right. Okay, and the next case, when D1 equals to 1, okay, and we want to hold D2 constant. We want to hold D2 constant because we're only changing D1. We're talking about the effect of D1 on Y while holding D2 constant. So D2 is constant, it is still lowercase d2. We put number 1 into all of these terms. So the second term becomes beta 1 because beta 1 times 1 equals to beta 1. And the last term becomes beta 3 times d2 because beta 3 times d1 is beta 3 times 1. And then times d2, lowercase d2. Now we subtract equation A and equation B. What we get is beta 1 plus beta 3 times d2, lowercase d2. All right, so what is this? This is the slope that we are talking about. Oops. Okay, so this is the slope we're talking about. The slope of, or the effect of x1 on x2 is a combination of beta 1 plus another term that is beta 3 times d2. Now, this slope is not linear because the slope depends on the value of d2. Because this slope contains d2. So if you change d2, okay, d2 is here. If you change the value of variable d2 or you change the value of lowercase d2, the slope is gonna change, right? So now if you change, so that means slope is nonlinear, okay? Or the slope is changing with some other value, okay? All right, so that is what we want. So B3, beta 3 is increment to the effects of D1 when D2 equals to 1. If you look at an example, you probably have a better idea about it. So now we have two variables. The first variable is D1, which is called high STR. It equals to 1 if STR is larger than 20, equals to 0 if STR is smaller than 20. D2 is high English learner. Oops. D2 is 1 if percentage of English learner is larger than 10%. It's 0 if it's smaller. Okay, so we can run a regression of D1, D2, and D1 times D2. Now we get the effect of high STR on Y, or on test score, when HI equals to, oops, when high English learner equals to 1, is minus 1.9. So it says that in high English learner district, if you, in a high English learner districts, that because our x variable is a binary variable, so the effect is a group difference. So the test score difference between a high STR and low STR school district is 1.9. While in a high, when high English learner equals to 1, which means in a high English learner districts, the difference between high STR and low STR school districts test score is 5.4. Okay, so what does that mean? That means STR has a higher effect on test score in a high English learner districts, while it has a lowered effect in a non-high English learner districts. Okay. All right. So what's the difference between interaction and what we learned before, the quadratic, cubic, or linear? log, linear, log, all of those things. So in the previous examples, all of those polynomial or log, the slope changes across its own value. It's its own x value. While here, the slope changes with the value of another x variable. Okay. All right. And is the interaction statistically significant? The answer is no. Okay. So what does that mean? That means even though what you estimated looks like reasonable, okay, or your story sounds reasonable, but your data doesn't have enough power to show that it is statistically significant. Okay, so in this case, you cannot reject the null hypothesis. You cannot say, oh, this is the story I want to tell. Okay, I don't have enough confidence to say that this is a story I want to tell. And it could be a lot of reasons. It could be that the interaction term is just not necessary, or it could be your data doesn't have enough power. Okay, it could be or other reasons, I don't know. Okay, but the thing is here that we want to interpret the slope to vary across another x variable values, which is d2. Okay. Oops. This page talks about, can you relate this coefficient to the following table of group cell means? The answer is yes. Okay, because okay, I know what this means. So look at beta 1, beta 3, and beta 1, beta 2, and beta 3, and think about what it means. So if you look at the difference between let's say 22, nope, 18. Okay, this one. Okay, so if you look at the effect of high and low English learner on in those districts with low STR, the difference between these two groups is exactly beta 1. Okay. See if it is right. 664.1 minus 645.9. Okay, I think so. All right. So beta 1 is the effect of high English learner on test scores, given that the school district is low STR or high STR equals 0. How about beta 2? Okay, beta 2 is slightly sneaky, but you can find out that it's here. I'm gonna change a color. Beta 2 is the difference between these two groups. Okay. So what's the difference? What's the effect of beta 2? Beta 2 is the effect of high STR, okay? Or beta 2 is the effect of high STR on test scores, given that high English learner equals to 0, because these two groups belongs to low English learner. All right, how about 3.5? 3.5 is slightly a little bit tricky, but you can think of it as difference in difference. Okay. I can think of beta 3 as difference in difference. Difference in difference is a very common term in econometrics if you go to graduate school. So what does difference in difference mean? So if you calculate the difference between each row, you're gonna end up getting, let's see, how much is this? The first difference we already know that is minus 1.9, right? Because it is the difference between low STR and high STR, given that English learner is low. That is the effect, that is the coefficient in beta 2. How about the second row? Okay, so the second row is probably, let's see, minus, whoops, I think it's 5.4. Okay. Oh, yes, that's correct. Okay, so that's the one difference. And if you take a difference between these two, all right, then that is 3.5. Okay. The difference between these two is 3.5. Okay, we call that difference in difference. It is the effect of beta 3, or it is the value of beta 3 hat. Okay. So this is how we model an interaction model between two binary variables. We have D1, D2, and D1 times D2. So the coefficient of D1 is the effect of D1 when D2 equals 0. Okay. And beta 2 is the effect of D2 on Y when D1 equals 0. Okay. And the last thing, beta 3, is the difference in difference. Okay. It's the difference in two groups and then take the difference between them. Okay. So you have minus 3.5, that is the interaction term, that is the difference in difference. All right. Okay. We don't have time to talk more about how we apply difference in difference in a lot of economics research. But if you guys are interested, I strongly recommend you to learn about it. Okay, so let's move on to our second case, interactions between continuous variables and binary variable. All right, so now we have a D and an X. In this case, D is binary, X is continuous. As specified above, the effect of X on Y holding D constant equals to beta 2, we want this beta 2 to depend on X. So we allow the effect of X to depend on D. So we include the interaction term D times X as a regressor. Everything is the same. We want to have two effects. We want to have the effect of X on Y when D is 0. We want to have the exact effect of X on Y when D is 1. So we put D equals to 0 and D equals to 1 into the regression. So then now we have two regression line. Okay, there is a D equals to 0 regression line, and there is a D equals to 1 regression line. Oh, how do we think about this? You can think of that. Sometimes we run wages on education, right? Effect of education on wage. So then the beta will be interpreted as an extra year of education on how much more money you earn. And beta 0 will be how much you earn if your education is 0. Right? And now you want to control for gender, and you also want the effect of education to depend on gender. Okay, let's say, okay, let's say a woman getting extra year of education will earn differently than a man having 1 extra year of education. So you have an interaction between female, okay, or gender as a binary variable on X, which is education, as a continuous variable. In this case, you can just think of them as two separate regression. Okay, you can just imagine that, oh, I'm just running two regressions separately, one for the woman and one for the man. Okay, so what does it looks like on graph? Okay, this is what it looks like on graph. We have two regressions, okay. One regression for man, one regression for women. So then we don't see D anymore because we already have two regressions. So D disappeared. We just have D equals to 1 as a line and D equals to 0 as a line. So you can have two regressions that have the same slope but different intercept, or different intercept, different slope, or same intercept, different slope. Okay. In this case, usually what happens is this one. Okay. Usually you will have a different slope and a different intercept because the data usually looks like this. Okay. Or in some case, you allow for the difference between it. Okay, unless let's see, unless there is some restrictions. All right. Okay. How do we interpret? Okay, this page is about how to interpret it. So now we don't interpret beta 3 as difference in difference, but we interpret beta 3 as the difference in slope. Okay, I should probably just require panel B. Okay, you guys still need to look at panel A and C. We'll just look at the panel B. So how do we interpret beta 0? Beta 0 is the slope for 0, okay? If 0 is if D equals to 0 is woman, then beta 0 is woman's regressions intercept. Okay, and if X is education, Y is wages, then beta 0 is women's wage without any education. How do we interpret beta 2? Well, beta 2 plus beta 0 is the wage for man without any education, right? So then beta 2 is the difference between these two intercepts. So beta 2 is the wage difference for two genders if both of them have no education. How do we interpret beta 1? Beta 1 is the slope for group 0. And beta 3 is the slope difference between these two groups. Okay. All right. I think it's very useful to remember this graph so that you have a visual idea about which, so you have a visual idea about all of the coefficients and what that means. Okay, this is very important if you want to interpret it. And we're gonna take a look at the test scores example again to see how we can interpret it. Okay. So for example, now STR is continuous. High English learner is binary. So in this case, you can think of high English learner as the gender. So now we have two regressions. The first one is for high English learner districts, and the second one is for low English learner districts. Okay. We have two regressions. We have two regressions. Which one is which? The first one is beta 0. So you can see that beta 0 is, let me change the color. So beta 0 is the slope for group 0. How about beta 1? Beta 1 is the slope for group 0. Okay. How about beta 2? Okay, beta 2 is beta 2 is the intercept difference between two groups. Okay, it's the intercept difference between two groups. And last one, how about beta 3? In this case, beta 3 minus 1.28 is the slope difference between two groups. Okay. All right. So how do we interpret it? It would simply say that class size reduction is estimated to have a larger effect when the percentage of English learner is large. Because when high English learner equals 0, the effect is only minus 0.97. While when the high English learner equals 1, the slope becomes minus 2.25. Is this significant? The answer is no. Okay, you can take these two. You can take beta 3 and a standard error of beta 3, calculate t statistic, and obviously it's not significant. Okay. All right, I'm not gonna calculate it, but it is not significant, even though your story is right. Oh, even the slope, the slope is not significant because t is only minus 1.3. The intercept difference is also insignificant because t is only 0.29. All right, so we can, oh, okay. So are the two regression lines the same? The answer is no, because if you test the last two variables all together, if you test these two variables all together in the f-test, it is significant, and we would reject the joint hypothesis, but neither individual hypothesis is significant. How could this be? Because two coefficients is correlated, right? We talked about this in the previous chapter. You can have both t statistics, you can have both beta not being significant, but they combine together being significant. And the reason for that is these two variables or these two effects is correlated. That's why if you test them separately, both of them are not significant, but if you combine and do an f-test, it's very significant. All right. Okay, last example. Interaction between two continuous variables. So if it's continuous, we use x. Now we have x1, x2, and we introduce a interaction term between x1 and x2. Now, if we change one unit, or if you change delta x1 units in x1, and then you subtract a and b, you end up having delta y divided by delta x1 equals to beta 1 plus beta 3 times x2. Okay, so that says the effect of x1 on y contains two parts. The first part is the beta 1. Okay, it's the original part, right? Originally, the effect of x1 on y is beta 1 in the linear function. But now in the interaction model, we have an extra part that is beta 3 times x2. So this says that an increment to the effect of x1 from a unit change in x2. You can think of, okay, let's just look at the example in the slides. Okay, again, it's still STR and a percentage learner, but in their continuous form. You run this regression, you calculate it, you get 3 betas, no, actually 4, beta 1, beta 0 all the way to beta 3. And if I ask you to write down effect of STR on test scores, it contains 2 parts. The first part is beta 1, which is minus 1.12. And the second part is 0.0012, beta 3 times percentage of English learner. Okay, so that says our effect of STR on test score contains first part, the linear part, and then the linear part, which depends on the value of percentage of English learner. Okay. So when percentage of English learner is 0, then this effect is minus 1.12. If percentage of English learner goes to 20%, this effect drops to minus 1.1. Okay. There are just 2 examples. And the question is beta 3 significant? The answer is no. Okay, the answer is no. See here. Oops. The answer is no because T statistic is only 0.06. How about beta 1? Beta 1 is significant. Okay, beta 1 is minus 1.9. Sorry, beta 1's T statistic is minus 1.9. So you cannot reject at 5% because it's not 1.96 yet, but close to it. Okay, you can reject at 10%. You cannot reject at 5%. Okay, so if you think 5% is your golden standard, then actually beta 1 is not significant. Beta 3 also is not significant. But do they combine tested significant? Okay. Which 2 are we combining? We're combining STR and the interaction term. Okay. We do an F test of these 2 variables combined, and we end up having a p-value that is 0.02, which is 2%, which is smaller than 5% level, right? So even though these 2 variables separately tested insignificant at 5% level, but if they combined, the F test shows that they're significant. So why is that? Because they're correlated. Or in some cases, we call it hyper imperfect multicollinearity. Okay, they're not perfect, but they are just very correlated. Okay, so you can think of that they're not perfect multicollinearity. Okay, they're not linear function of each other, but they contains very similar information, so they eat each other's effect. Okay, that's how I understand it when I was learning this. Think of them, they are fighting for the effect together. So separately, they both tested negative. They both tested insignificant, but they combined F test is significant. Okay. The last part, I'm not gonna cover it. It's an application example that to explore nonlinear effects on test scores of the student-teacher ratio. So the question is, are there nonlinear effects of class size reduction on test scores? And are there a nonlinear interaction between percentage of English learner and student-teacher ratio? So we already answered all of these questions, but in these examples, it also explored a lot other situations. Okay. See, so you can have str square, str to the power of 3. You can have percentage of English learner as continuous variable or binary variable. And then you can have binary variable interaction with str as continuous. You can even have binary variable times a quadratic term as interaction. Okay. And there is all of these F tests that you can take a look at to have an idea about how we chose between models. Okay. At the end, there might not be perfect answers. That is the fun thing about econometrics. You don't make decisions based on data. You also make decision on intuition, on explanation, on its realistic sense. It's a combination of both. Okay. All right, so that's it for chapter 8.